This question comes from Vittorio, who asks what would happen if a glass of water were suddenly literally half empty. And in that case, the pessimist might actually be more correct than the optimist. When people say a glass is half empty, they usually mean it contains equal parts water and air. Traditionally, the optimist sees the glass as half full, while the pessimist sees it as half empty. Linguist Ketchen Molik points out that this difference is really about reference states, a shortcut language uses to indicate whether the glass is being filled or emptied, and language is pretty cool. But what if the empty half of the glass were truly empty? A perfect vacuum. A vacuum would not last long, but what happens depends on a question nobody usually asks. Which half is empty? Imagine 3 scenarios: a normal glass with air and water, a glass with vacuum above the water, and a glass with vacuum below the water, with the vacuums appearing at time 0. For the first few microseconds, nothing happens, because on that time scale, even air molecules barely move, although some travel at hundreds of meters per second, and the fastest exceed 1,000, and those are the first to drift into the vacuum in the top vacuum glass. In the bottom vacuum glass, air cannot get in, and while water does not expand like gas, in a vacuum it starts to boil, releasing vapor. In the top vacuum glass, the water also begins to boil, but incoming air stops it. After a few hundred microseconds, air rushes into the top vacuum, slams into the water, and sends a pressure wave through the liquid. The glass flexes but holds, and the shock wave bounces through the water and air, spreading to the other glasses and reaching a human ear as a loud bang a few milliseconds later. Around this time, the bottom vacuum glass starts to lift, because air pressure at sea level is about 15 pounds per square inch, meaning nearly 100 pounds of force on the water and glass, normally balanced by air pushing up from below. But here there's no air underneath, so pressure pushes the glass up and the water down, creating what we call suction. In the top vacuum case, the effect is too brief to matter, but in the bottom vacuum case, the glass and water accelerate toward each other, and even though some vapor forms, it cannot cushion the impact. In under 10 milliseconds, they collide at several meters per second, and the water slams into the glass bottom like a hammer. Because water is almost incompressible, the force is sharp and enormous, the same water hammer effect that causes pipes to bang or lets you knock the bottom out of a bottle by hitting the top. Here the force is enough to destroy even thick drinking glasses. The bottom breaks, hits the table, and sprays water and glass shards everywhere, while the top half of the glass continues rising, hits the ceiling, shatters, and falls back down. So if the optimist says the glass is half full and the pessimist says the glass is half empty, the physicist asks which half. But there is an even deeper lesson hidden in this thought experiment, because the whole situation shows how fragile our everyday assumptions really are. We casually talk about empty space as if it is nothing, but in physics, nothing is one of the most violent things you can imagine. A vacuum is not just the absence of matter, it is an imbalance, and the universe really hates imbalances. The moment you create a vacuum, everything around it tries to erase it as fast as possible, whether that means air rushing in, water boiling, or glass exploding. This is also why space is so dangerous for humans, not because it sucks you in like a vacuum cleaner, but because your body is full of pressurized fluids and gases that suddenly have nothing pushing back. Even small pressure differences can do dramatic things, like crushing submarines, bursting balloons, or collapsing containers. In the glass example, all we did was remove half the pressure, and we got shockwaves, flying glass, and ceiling impacts in milliseconds. And this isn't just theoretical. Engineers deal with pressure differences all the time, from designing soda cans and vacuum chambers to building spacecraft and deep-sea vehicles. So next time you hear someone argue about whether the glass is half full or half empty, remember that both of them are ignoring the real danger. Because if half of that glass were truly empty, physics would turn it into a tiny explosion. And what makes this even cooler is that this whole scenario connects to some of the biggest ideas in physics, like thermodynamics and quantum mechanics. Even in a so-called perfect vacuum, there is still energy, tiny fluctuations popping in and out of existence, meaning true nothingness might not even be possible. In real life, creating a perfect vacuum is insanely hard, and every vacuum chamber on Earth still has stray atoms bouncing around. That's why scientific equipment like particle accelerators and electron microscopes need massive pumps and complex systems just to get the pressure low enough. A half-empty glass experiment is basically a miniature version of these extreme environments, where pressure differences dominate everything. It also shows how intuition can fail us. Because we think of water as heavy and solid and air as light and harmless, but in large amounts, air pressure can bend metal, crush submarines, and shatter glass in milliseconds. Physics often takes everyday ideas and pushes them to extremes just to reveal what's really going on underneath. So the glass half full. El debate isn't really about optimism or pessimism. It's about how language, intuition, and reality all describe the same thing in completely different ways. And sometimes the universe has a very dramatic answer waiting if you change just one assumption.